To understand collisions in one dimension, you have to first understand conservation of momentum. And conservation of momentum just simply says preservation from loss. That's what conservation means. It means it's not going to go anywhere, it's going to stay in the system. So using conservation of momentum, do you think we could predict what is going to happen when these two carts collide into each other? Well, if momentum is conserved, the total momentum before they collide is going to equal the total momentum after they collide. It was conserved. And if you can simply say before equals after, then you should have no trouble saying this. That's just the Greek letter sigma, represents the sum. And remember, P is our abbreviation for momentum. So this is just the sum of all the different momenta initially. And momenta is plural for momentum. And that should equal the sum of all the individual momenta finally, or just before equals after. Total before equals total after. And if you can say that, you can say one of two things. Because there's two ways that these carts could collide. They could collide and bounce off of each other, and that would be an elastic collision. Elastic is like stretchy, bouncy. Or if they collide into each other, they could actually stick together, and the prefix in means not bouncy. So these two carts have Velcro that will be able to attach the carts and make an inelastic collision. If you flip the carts around, they're very powerful magnets that will repel the two carts, and they will bounce off of each other, not actually having physically touched each other. So this is the big idea. Total momentum before equals the total momentum after. When we have an elastic collision, remember, if we can say this, we can say this, so we should have no trouble saying this. If there's just two carts here, the momentum of the first cart added to the momentum of the second cart before the collision should equal the momentum of the first cart plus the momentum of the second cart after the collision. And if you can say that, you should have no trouble saying this. Because remember, momentum is mass and velocity. So the mass of the first cart times the velocity of the first cart, that's the momentum of the first cart. That's the momentum of the second cart, added together, total before, and should equal the total after. If these two carts collide and stick together, we don't have two separate things with momentum after the collision. We just have one thing. So this is the momentum of one plus the momentum of the other before, but afterwards they stuck together, and this is just the combined momentum of both carts 1 and 2. If you can say that, you should be able to say this. All it is saying is that before the collision, this had momentum, and this had momentum. Add them together, that's the total momentum. But after the collision, the mass of one stuck to the mass of the other, and the combined mass moved off at one velocity. Those are our two really big equations in this video. I've got to make sure we're using those two equations. Okay? So, we're going to collide these two carts inelastically. The Velcro is going to grab hold of these, and they're going to stick together. And I've got 1 kilogram moving at 1 meter per second to the right. Okay, so velocity is a vector quantity, so velocity to the right would be positive. And then this car is 1 kilogram moving at 1 meter per second to the left, so negative there. And watch what happens. That was exciting. They just stuck together. So after the collision, I had 1 kilogram moving at 0 meters per second, and the other mass was also stopped. Okay, let's just check to see conservation of momentum. Did it really stay conserved? So the sum of the momenta before equals the sum of the momenta after. Okay, and they stuck together. So the one cart plus the other equals the combined mass of the two, and the momentum of the combined mass of the two. So that's our equation that we've just talked about. I plug the numbers in. I've got 1 kilogram moving to the right at 1 meter per second, and 1 kilogram moving to the left at 1 meter per second. Afterwards, I have 2 kilograms that stopped. And if I do that, this times mass times velocity is 1 unit of momentum, and mass times velocity is negative 1 unit of momentum. And 2 times 0, 1 plus a minus 1 is 0, and 2 times 2 is 0. Momentum was conserved. And that's a little weird because the total momentum before the collision was 0. And that's because they were moving in opposite directions. Momentum is a vector quantity, okay, just like velocity is. Momentum to the left is negative, momentum to the right is positive. Okay, so momentum was conserved. It was the same before as it was after. Now, kinetic energy, remember K is our abbreviation for kinetic energy. Kinetic energy is just one form of energy. There's potential and there's heat and sound and light and all that. But what I'm saying here is that if we take the total kinetic energy before the collision, it will not equal the total kinetic energy after the collision. Momentum is conserved, but kinetic energy is not. Let's see why. If I just take the kinetic energy of the first cart and add it to the kinetic energy of the second cart, I'm saying that it does not equal the combined kinetic energy of both carts. And let's see why. Well, here's 1/2 mass times velocity squared is kinetic energy of one cart, kinetic energy of the other cart, and 1/2 the combined mass moving at that velocity squared. So I plug in the velocity. I had 1 kilogram moving at 1 meter per second and 1 kilogram that was moving at negative 1 meters per second. When I square this term, I take 1 times negative 1 squared and then multiply by 1/2. That term there is just going to be 1/2. And that term there is also going to just be 1/2. But 0 squared is still 0, so 0 times all that is still 0. So after the collision, the total kinetic energy was 0, but before the collision, it had a kinetic energy of 1 joule. And the reason for that is that kinetic energy is not a vector quantity. We don't say we have kinetic energy left and kinetic energy right. It just, this has some kinetic energy and that has some kinetic energy. So we take the total kinetic energy. You don't have negative kinetic energy. So the kinetic energy was not conserved. We lost 1 joule of kinetic energy in the collision here, even though momentum was conserved. And that's one important thing, is that in an inelastic collision, kinetic energy is not conserved. These things want to bounce off of each other and fly apart, but the Velcro is holding them together and doing work, converting kinetic energy into other forms of energy. So here's some old steam engines. They're going to collide into each other, and we see that the total momentum after they collided was 0. So the total momentum before they collided was 0. And they had a bunch of kinetic energy before they collided, but all that kinetic energy was transformed into something else because of the force and the distance that was done in mangling these two engines. The work that is done, some of that work is done in what's called lasting deformation. When you permanently deform an object, well, it takes work to do that. And some of the kinetic energy would be transformed into something else. Molecular vibrational kinetic energy. The molecules that make up that engine are going to start to vibrate more, and that's what we know as heat. Sound and light and all sorts of other forms of energy. So if this ball collides into this block, is kinetic energy conserved? Okay, the ball was deformed and bounced back. Was kinetic energy conserved? And yes, it actually was, because the ball was only momentarily deformed. It wasn't lasting deformation. Now, squeezing the ball like that is going to make the molecules vibrate a little faster, and the ball's going to warm up a little bit. So maybe some of the kinetic energy was transformed into heat, but for the most part, it's conserved. Okay, let's look at the momentum of this before the collision. if this has 1 kilogram meter per second, so this is the combined mass and velocity of one unit of momentum, and this is initially stopped, so it has 0 units of momentum. Afterwards, this thing bounced back to the left at, say, negative 0.5 units of momentum. How much momentum should this have after the collision? It's going to be 0.5 or 1, or what do we think? It's going to be 1.5. And the reason for, the total before is those added together, and it should equal the total added together after. So before equals after. One just kind of mind-boggling thing is this is how much momentum the ball had before the collision, and the block here had more momentum after the collision than the ball had initially. But that's because the ball ended up with negative momentum going back to the left. All right, this is just the reverse of the previous example where the carts stuck together. But in an inelastic collision, there's a spring holding these apart, and I'm going to just release it and they explode like that. But 1 kilogram was stopped, another kilogram was also stopped, and it's just the reverse. These were initially stuck together and then they separated. But the total momentum before should equal the total momentum after. So we had the 2 kilograms that were initially stopped. The blue one moved back to the left. The blue cart moved back to the left, and the red cart moved back to the right. 2 times 0, negative 1 and positive 1. Momentum was conserved. Okay. Now these have different masses on them. This one is 1 kilogram that's initially stopped, and this is 3 kilograms that's also initially stopped. It's going to be different in this case. Do you think momentum is still going to be conserved? What's going to happen to this cart here that has 3 times as much mass? Well, it might have 1/3 as much velocity. Okay, and we're not measuring that, but it looks to be about 1/3. So we just plug the numbers in. We had 1 kilogram and 3 kilograms combined initially, and they were stopped. And then if this one went off at 1 meter per second to the left, that other one must have gone off at 1/3 of a meter per second, because this gives us negative 1, that gives us positive 1. Before was 0, after is going to be 0. Momentum is conserved. Okay. Now we're going to have this one initially stopped. So we have 2 kilograms that's initially stopped, and this 1 kilogram is going to be moving in. Instead of me playing the video for you first and then seeing what happens, one of the cool things about physics is its predictive nature. I know what those carts are going to do before they do it. Okay, I can predict what's going to happen. So let's use this equation to predict what the velocity of the 2 carts together is going to be. It's inelastic. So initially we had 2 kilograms that was initially stopped. We had 1 kilogram moving to the left at 1 meter per second. And then afterwards, the 2 kilograms is going to combine with the 1 kilogram, and they're going to move off at some velocity. And I want to know what that velocity is. So 2 times 0 is 0. 1 times negative 1, a total of negative 1 before, equals 3v. So if I divide both sides by 3, I get the velocity is going to be negative 1/3. That negative means that when this cart collides, it's going to go off to the left at 1/3 the velocity of that one. Let's see it. Seems reasonable. Seems to be about 1/3 the velocity. And we could so measure that. In fact, we will do a lab in the next video that does measure that. The interesting thing about inelastic collisions, if you're going to make predictions, is that there's only one variable to solve for. Inelastic collisions only have one variable to solve for, so it makes it kind of easy algebraically to solve for that. Okay, but if I have an elastic collision where these two bounce off each other, if I knew mass and velocity before and mass and velocity afterwards, I want to find out how fast this one is going and how fast that one's going afterwards. So I have 2 velocities to solve for. So now we're looking at elastic collisions, where the masses did not combine, but afterwards we still have cart number 1 with some momentum and cart number 2 with some momentum, but they should add together so that the total before equals the total after. Okay, so we plug the numbers in. We got 1 kilogram that's initially stopped. We got 1 kilogram that's moving to the left at 1 meter per second. That's this one coming in like this. But afterwards, I want to find out what those two are. And I said it complicates things dramatically, and you might see that it does. Except this example I've given is kind of straightforward. What happens is, can you see what happens there? All they did was swap velocities. And that is true only if they have the same mass. So if the masses are the same before, then the one that was 0, the blue cart was 0, now the red cart will be 0. And the red cart was -1 before, the blue cart will become -1 after. Okay. Big idea there is that when the masses are the same and they collide elastically, they simply swap velocities. So let's do this one. This one's 1 kilogram moving at 1 meter per second to the right. There we go. And then this one is 1 kilogram moving to the left at about half of a meter per second. So this one's moving about twice as fast as this one. Let's see if it's going to happen fast, but let's see if we can see that they really do just swap velocities. Kind of hard to see. So let me show you that they did, and then I'll show you in slow motion. Well, the blue cart was moving to the right at 1 meter per second before, and then the red cart was moving at 1 meter per second after. The red cart was moving to the left at half a meter per second before, and the blue cart was moving at half a meter per second after. To help us see this, I'm going to show this is a vector representing the velocity of the red cart and the velocity of the blue cart. See how it's about twice the velocity of this. Watch what happens. Really just the red cart got the blue velocity and the blue cart got the red velocity. Okay, so when they have the same mass in an inelastic collision, it's as simple as swapping the velocities. All right, now, okay, I want to take a deep breath here because we're going to fill this lower area here with a bunch of math, a bunch of algebra. It is still just simple algebra, and sometimes you look at what you need to do in algebra and you think, oh, I really don't want to do that. But you take a deep breath and think, I can do it. So let's do it. All right, this time, this is 2 kilograms. I got a little mass on top there. So I've got 2 kilograms that's initially stopped, and then I've got 1 kilogram over here moving to the left at 1 meter per second. And I'm not going to play the video until we calculate what's going to happen. Okay, so we plug in the numbers. 2 kilograms initially stopped, 1 kilogram moving to the left. Afterwards, the 2 kilogram mass, we want to find out its velocity, and the 1 kilogram mass, we want to find out its velocity. All right, we have 2 variables here. Okay, and in algebra, anytime you have 2 variables, you need 2 separate equations. And you're going to solve those equations simultaneously. The second equation is conservation of kinetic energy. But wait, you said kinetic energy is not conserved. Kinetic energy is not conserved in inelastic collisions, where they stick together. That Velcro had to hold them together and do work, converting kinetic energy into heat and sound. But when they are free to bounce apart, kinetic energy is conserved. So the total kinetic energy before should equal the total kinetic energy afterwards. So kinetic energy is 1/2 mass times velocity squared. That's the kinetic energy of the first cart, added to the kinetic energy of the second cart, and the total before should equal the total after. And this is where you might want to start to take that deep breath. but we plug in the numbers. I've gone ahead and there's a half here, a half here, a half here, and a half here. There's a half in every term, so I just canceled out the half. Multiply everything by 2. So I've got 2 kilograms stopped, and it gets squared. Here's the mass, velocity, and it gets squared. Mass and velocity squared, and mass and velocity squared. All right, so here's one equation with 2 variables. Here's the other equation with 2 variables. So we take a deep breath and say, I can do this. What we always do is we solve one of the equations for one of the variables. So I'm simplifying this down here. This equals -1 on this side, and then I'm not even bothering multiplying by 1. So I'm going to take that equation and solve for one of the variables. I'm going to solve for v sub 2. I'm going to subtract 2v sub 1 from both sides. So that's one of the equations solved for one of the variables. Then you know what to do. I pause there so you can do this. You're going to substitute that. There's v sub 2. I'm going to substitute all that right in here for v sub 2. Okay, so that's v sub 2 right there. And we got to be careful with our algebra. This thing gets squared, and you have to FOIL that out. You take the first, outside, inside, and last, and FOIL that out. Okay, so you take the first terms, outside terms, inside terms, and let me see, I just forgot what. Let me back up to right here. When we FOIL that out, that times that is 1, this times this, plus this times that is this, and that squared is this. Okay, now I'm going to combine like terms. This has a v squared in it, that has a v squared in it, so we're going to get 6v squared, and then we have 4v sub 1, that's here, and 6v squared, that's here. I subtracted 1 from both sides to get 0 here. Then this term here, I have a v sub 1 in both terms, so I'm going to factor that out, and that's what I'm doing here. If you distribute that back in, you get the same thing as you had over here. So what could v sub 1 be so that this equals 0? Well, if v sub 1 equals 0, 0 times whatever that is will still be 0. And then if I set this term equal to 0 and solve for v sub 1, I could find that -2/3 would be true as well. Well, we already know that it works if v sub 1 is 0 because v sub 1 was 0 here, and that would make before equal after, but it's not very interesting. So I'm going to go with this one. V sub 1 is -2/3. So I'm going to plug in -2/3 v sub 1 right here for v sub 1. I multiply that out, I get +4/3, and -1 plus 4/3, so that's -3/3 plus 4/3 is +1/3. We just did it. We figured out that after the collision, the blue cart here is going to be moving to the left at 2/3 meter per second. The red cart is going to be moving back to the right at 1/3 meter per second. So, and then, 2/3 is twice as fast as 1/3. So when these two collide, this is going to be going twice as fast. This is going to be going twice as fast that way as this one was going back that way. Here it goes. That's going twice as fast to the left as that one was going to the right. Okay, twice as fast to the left as that one's going to the right. We could do it again. I'm not going to. I'm going to say, hey, hit pause here, and it would be really good to practice this. So let me just tell you, I've done all that same math that I've did in that previous one. And I've changed the initial conditions here. Instead of, this one was 2 kilograms before, but now this one's 2 kilograms. I just moved the mass over here. So let's see doing all that crazy math, I find that V1 is going to be going to the left at 4/3 meter per second, and V2 is also going to be going to the left at 1/3 meter per second, which means this is going to be going to the left 4 times faster than that's going to the left. Let's check it out. Totally predictable. Isn't that awesome? All right, Newton's cradle. And I used large ball bearings here. I welded a clip on there so that I could attach my cables. And they're, probably 2-inch diameter balls here. But Newton's cradle, if one ball goes in, one ball goes out. Okay, that's the only way it could work. If 2 balls go in, 2 balls go out. If 3 go in, 3 go out. What happens if 4 go in? Well, 4 should go out. That's pretty cool. And if 5 go in, 5 go out. Oh, what if 6 go in? Ta-da! 6 go out. Okay. But what would happen if one ball collided in at some velocity and 4 balls went out at 1/4 the velocity? So it's like 1 kilogram moving at 1 meter per second equals 4 kilograms moving at 1/4 of a meter per second. That is totally okay. No problem there in terms of conservation of momentum. But if you do that also with conservation of energy, take the kinetic energy of this and the kinetic energy of that, the numbers don't work. So if one ball comes in like this and 4 go out at 1/4 the velocity, not going to happen. I had to doctor that video to make that happen. So that's Newton's cradle. And when the balls come in, not only does momentum need to be conserved, but kinetic energy needs to be conserved as well. And the only way to make both of those conservations work is if one comes in and one goes out, or 2 go in and 2 go out. Big idea behind collisions in one dimension is that the total momentum before equals the total momentum after. 2 ways they could collide: elastically or inelastically. And that's a little bit about conservation of momentum collisions in one dimension.